Welcome, this is my grade advancers and I welcome you again to my video lesson on forces and their interactions. Okay, so in this video, we shall be looking at how forces shape the world around us. But before we begin our exploration, I would like us to understand the fundamental concepts of vectors and scalars. So, what exactly are vectors and scalars? And why are they essential in your understanding of forces? Well, let's start with uncovering that because that's exactly the point we should start from. Now, I would like to tell you that vectors are quantities that has both magnitude, they have both magnitude and direction. While a scalar is a quantity that only has magnitude. It has magnitude but no direction. Now, when we start to identify something like in this tags here, we are going to separate some quantities into scalars and vectors. Okay, we're going to separate some quantities into scalars and vectors. And at the end of the day, we would see and understand some simple things on how to understand these quantities. Now, look at what you have here. And what we have here, we have quantities like power, distance, mass, time, acceleration, velocity, and force. Now, I will start by writing the quantities that are there. Here, we can have the mass of an object, okay, which is a scalar. Distance is also a scalar. And energy, of course, energy is also a scalar. And of course, time is also a scalar, okay? Time is also a scalar, and speed is also a scalar quantity. What else is a scalar quantity? Now, don't get it wrong. Don't think all the quantity that we have here are scalars. No, of course not. They are not all scalars. However, how do we come to realize that these quantities are scalars? Number one is by studying, okay? When you study and you know that these particular quantities, they are scalars, you'll get to know them. The other thing is also making a research yourself to be able to understand why a particular quantity is a scalar and why the other one is a vector. Okay, now the first one is by their definition, you can really understand why a particular quantity is a vector and why the other is a scalar. Now, for example, the mass of an object. When we want to write the mass of an object, we write it as 5. Maybe I'm giving an example now. Maybe the mass of an object is 5 kilograms. Now, I've seen students mix the idea, they just get it mixed up. They will think just because we have written a unit behind a number, that number should be a scalar quantity, a vector quantity or something. No. Okay. The unit gives you an idea of what quantity was measured. So when I see kilogram behind any number, I know, okay, the quantity actually is talking about mass because kilogram measures mass. Kilogram or gram or pound, whatever you have, is a unit associated with the mass of an object. Okay, now, however, there is no, because if we look at the definition of mass, mass is just the quantity of matter present in a body. There is nowhere to see, well, maybe the mass of an object has a direction. Now, the easiest thing to confuse with mass is weight. I do not have weight in this quantity, but of course, the weight of an object is a vector quantity and not a scalar. The unit of weight is newtons. So if I say 5 newtons and 5 kilograms, of course, by value, by the size, we said a scalar quantity has only size. The size of this is just 5. On the other hand, weight is not just 5. Of course, the size of the weight is 5 newtons. We have talked about the number and the unit being the size, okay? 5 newtons, the unit is telling us what type of quantity it is. That it is a quantity that measures force, which is newtons, and the size of that is 5. However, the direction of weight, the weight of an object is always downward, okay? It's always acting downward. So if you are seated on a chair, your weight has a direction and is acting downward, okay? Because your weight is pushing on the chair, so your weight is acting downward. So do you start to see that, of course, the weight has direction, all right? Now, when you also think about distance is also a quantity we can measure with units, and that is 10, for example, 10 meters. 10 meter is the unit of distance. It's a unit of distance, right? So, and it has no direction. If you say, well, the boy ran 10 meters. If he ran 10 meters, he could have run 10 meters anywhere in the world. That's distance, okay? But when you say something like he ran 10 meters at school, do you get? Now, you have the school in that case has given you a direction. Now, different from when you say the boy ran 10 meters. He running 10 meters could be anything. Could be, it could be anywhere. It could be in Canada. It could be in any part of the world. Okay, but when you put a direction, when you give a direction to distance, okay, it is no longer a vector. Then we call that displacement. We call that displacement, and displacement is a vector quantity. So if I write something like 5 meter north, or sometimes we can use signs, either say negative 5 meters, or 5 meters, positive 5 meters. All of this symbol is telling you they are vectors because this is the symbol in front of the number. The signs there are telling us the direction. So on and on we can go. Again, we've said that speed is a scalar quantity, and force will be a vector quantity. Velocity is a vector quantity because it has magnitude and direction. Power is a scalar quantity, okay? And that's all that we've gotten here. You can write any other quantity to check if they are vectors or scalars. Now, if you are gotten an understanding of the types of quantities that are vectors and the type of quantities that are scalar, then you have done excellently well. Now, let's get going. It will interest you to know that for vector quantities let me start with scalars. For scalar quantities, we don't do lots of mathematical calculations, okay? We just solve them simply, and there we go. That is, we solve them simply by adding. So if you have, if somebody tells you the mass of 20 people is, maybe it was given like the mass of 20 people are 5 kilogram, 10 kilogram, 20 kilogram, and on it goes. And the person is asking the question, what is the total mass? What you just do is you add all of these masses together as 5 plus 10 plus 20, and you get 35. And that's all about scalars. But it's not quite easy with vectors like that, as we're going to see in this example. Okay, it's not quite easy with vectors like that. You have to do more for vectors because they have direction. So here is a man walking 10 kilometers north, and 10 kilometer east. And we have to look at the fact that there is a representation, okay? The man walks 10 kilometer to the north. So this is not just a distance. It's not saying, if the questioner says something like, a man walks 10 kilometer and then he walks another 10 kilometer. All of those are distance, and the total distance he had walked will be 20 meters. However, when it involves vector, because there is direction, the man had walked 10 kilometer north here, and then he walked another 10 kilometer to the east here, okay? And, for you to remember, these are the cardinal points. Your north is here, and this is the east, this is the south, and this is the west, okay? So that's what should guide you in drawing a representative diagram like this. Now, this man walks 10 kilometers to the north and another 10 kilometers to the east. Now, of course, the next question would be, how do we find the displacement? This is not distance. If the question asks us, what is its distance? Distance will be 10 plus 10, and that will be 20 kilometers. That is distance. However, displacement has to do with something from a starting point. This was his starting point, and this was his final point. So the difference between his starting point and his final point is what gives us displacement. But however, when you look at the path he has traveled, he had traveled a path that looks like a right angle triangle. So now the displacement is this blue line. We have to complete the shape to have a right angle triangle so that we can apply Pythagoras theorem by saying 10 squared plus 10 squared, okay, is equals to the displacement. If we call the value of the displacement x squared. Now, you have to remember that Pythagoras theorem says hypotenuse squared is equals to opposite squared plus adjacent squared. Now, the longest side is the hypotenuse. The opposite is either of this line. So the other two sides are the opposite and the adjacent. So we have opposite square and adjacent square. The opposite, one of the side is 10. The other side is also 10. So 10 plus 10 square and 10 square. 10 squared is 100 plus another 100, and that will be x squared. And of course, x squared would be square root, x squared would be, that's a quite jump, okay? I want to follow it step by step. X squared will be 200, 100 plus 100 is 200. And if we do that accurately, you now find the square root of 200. What is going to be the square root of 200? If you use your calculator, the square root of 200 will be 14.1 kilometers, which is what we have here. Now, if you have any question, could you let me know? Okay, so moving forward, we want to start a discussion about forces. And let's look at what is a force. A force is a push or a pull, okay? A push or a pull is what we regard as force. And it's also very interesting to know that we have 6 different forces. 6 different forces are important for you to know about. You have to know about 6 different forces in physics. And let's talk about each one of them, just to mention them one after the other. Now, one of them is the force of gravity. Now, this force has a lot to do in physics, and we will look at that later on. And then we have the reaction force. The force of gravity, for you to keep that in mind, is what you feel with your weight, is one of the forces we use to determine the weight of an object, is also the value we use when we are talking about acceleration due to gravity. And there will be more interesting things to talk about in each type of these forces. So then we also have the reaction force, right? Reaction force. It's this kind of force that, when you are seated, I said earlier that your weight is acting downward. Now, there will be another reaction force acting upward, which is like a counter effect to the weight of your body. So if your weight is going downward, then the reaction force will be going upward. Okay, so that's the second type of force that we are going to be learning about. Another type of force that is important is the force we call thrust. Okay, this is another type of force. Okay, and thrust could be a push, it could also be a pull. So whatever you want to call that, maybe like a compression force or an extensive force. So we can talk about, so thrust is another type of force. Another type of force is the force of friction. That's frictional force. And frictional force, either it involves drag or air resistance, we are calling that frictional force. And this is a type of force that slows things down. So if you are pushing an object in this direction, okay, there will be another force acting in this direction to slow the object down, and that is the force of friction. Okay, so these are just simple things. We're going to look at them in more details. So, and the other type of force we should look at should be lifts. The force that is due to lift, and these are forces that we talk about in an aeroplane. Okay, is due to an aeroplane wing, and we're going to also see that at a later time. And the last one, but not the least, is the force of tension. Okay, this has nothing to do with the tension you have maybe when your test is coming. No, this is a tension we find in rope. So if, for example, in the game of tug of war, or when you are trying to draw a rope, you have tension in those ropes. So these are the 6 different forces you have to know about, or you have to learn about in your journey about forces. Okay. Now, can we look at the question we have here? It says, what forces do this picture represent? So from all the things I have said, what would you say are the type of force each of these pictures represent? I have given you the 6 different forces that you should know. So can you say which of them? Yeah, excellent. This is the weight. Okay, this has to do with weight of an object, and if we want to look at that, it has to be with the force of gravity, because the weight of an object is due to the gravitational pull of the earth upon a person. So this has to do with gravity. What about this? What about this? Good. That is air resistance. This is a skydiver. This is air resistance. The air resistance will try to slow this person down, the skydiver down, from falling headlong. So this has to be a force which we can call air resistance. Okay. What about this? You see, of course, you can think about that. The car is moving forward, and there is another force going backward. What do you call that? Yes, friction. Well done. That's the force of friction. Friction slows the motion of an object down. And what about this last one? What would you call that? Can you leave your answer for me in the comment section? And then I'll see that. Thank you. Okay, so that's the introduction I should start with in looking at the definition about forces. Now, before we move on, you also need to learn that all of these forces we have talked about can be grouped into 2. Okay, they can be grouped into 2. They can be grouped into contacts and non-contact force. Okay, non-contact force. So what do you remember? What do you think is a contact force? And what do you think is a non-contact force? Yeah, from the word the meaning is what it's intended. Contact force means something has to come in contact. They have to touch. There has to be a touching, okay, before the effect of the force will be felt. But when we say non-contact, you don't have to, the forces don't need to touch the object or come in contact with anything before the effect will be felt. So that is just a simple way to remember those definitions. So let's come to the next thing, which is looking at contact and non-contact forces. So which of these would you regard as a contact force, and which of these would you regard as a non-contact force? Okay, can you make your classification? Well done, well done. Okay, now the force of friction. Friction is, of course, a contact force. There is no doubt about that. It's a contact force. The object has to come in contact. Okay, if we want to have friction between a car tire, it has to touch the ground for us to experience friction, because we talk about friction when two surfaces are in contact with each other. So that's a contact force. Okay, and what about air resistance? What do you have to say about air resistance? Is it a contact force or non-contact force? Yes, it's a type of friction. It's a contact force because it has to do with air pulling back on something, and it has to come in contact. Okay, like in the example of the skydiver, the skydiver will feel the air, or it's just like, let me give you this idea of you using your umbrella during a storm. You feel like, okay, there is some air inside the umbrella trying to drag the umbrella away from your hand. So of course that should be also a contact force. So I will use C to represent contact to save time. And gravitational force, yeah, we don't feel that, okay? We don't feel it before the effect is being felt. Okay, so that is non-contact, okay? What about tension? Tension, of course, is contact, because you have to, before a rope will feel a force, there has to be a pulling from one hand or both ends for you to feel the tension. What about electrostatic forces? Yeah, they are not good. So electrostatic force, of course, is non-contact, okay? It's non-contact, it's not a contact force, it's non-contact. These are forces around an electric charge, okay? They don't have to come in contact before their effect is felt. It's the same thing like with magnetic forces. A magnet is also a non-contact, and reaction force is contact. So a magnetic force, just like electrostatic force, they are non-contact. When we place a bar magnet, okay, if I place a bar magnet and then I have a spoon and I'm bringing them close to each other, the magnet does not have to come in contact with the spoon before the force of attraction will be felt, okay? So that's what we mean by contact. And on the other side, when you talk about reaction force, when you are seated, the force is also pulling back. Now, talking about contact or non-contact, we are not talking in terms of either you can see them. We cannot see friction, of course, but we know friction can be felt when two surfaces are in contact. We cannot see the air resistance, but we feel it, right? That, okay, there is a particular force pulling back something, okay? And gravitational force, it's the force that pull objects down towards the center of the earth. So when you throw things up, they naturally come down, right? Without having, this is not about the air resistance, either there is air or no air. When you throw objects up, they tend to fall back to the ground. And tension, again, we said, is the force that is felt in a rope. So now, I believe with this understanding, you understand again that forces are classified into contact and non-contact forces, okay? And non-contact. So if you have a question again, please do leave it in the comment section. So let's now start to talk about each of these forces, and this is where it's getting more interesting. All right. So keep following for you to enjoy all of this content. And remember, I am able to differentiate a content for you, a lesson for you to meet your educational needs. So if you need that, you can send me a message and we'll talk about how we can be of help to you. Now, let's talk about the big thing, which is not really big, but it has become something over the years that people drag. And that's something that has to do with weight and mass. In daily usage, people will talk about mass, they will talk about weight when what they are talking about is the mass of the object. And it's just a mix up. So if you are a student who is familiar with this thing, then when you come to physics, you have this little confusion and you have to quickly clarify that. In physics, mass and weight are not the same, okay? The weight is the Earth's gravitational pull on an object, okay? So, and the force of gravity, like we started to talk about, is the force of attraction between all masses. That is, every object that has a mass, we experience the influence of the force of gravity, that is the gravitational field strength, or whatever you want to choose, either the force of gravity or gravitation. So the force of gravity attracts all masses, but you only notice it when one of the masses is really big, okay? But if the mass is so small, like say the mass of an electron, let me use an electron now. An electron is so small that the mass is neglected. So you will not feel that, or say the mass of an atom is so small now. So now you will not feel that the mass of such an object. So now it's only felt when we have bigger objects. Bigger objects will experience the force of gravity. They will feel it more strongly. Another thing for you to remember about force of gravity is that it makes all things accelerate towards the ground. So when you throw an object up, when you throw a ball up, okay, so the force of gravity will make the ball to accelerate towards the ground. And that's how easy it is. Another thing is it gives everything weight. So you can see that the force of gravity is really important. It gives everything weight. The weight of an object is as a result of the gravitational pull upon the mass of an object. And also, the last thing I will say about it is that it keeps planets, moons, and satellites in their orbits. So it's the weight of an object that keeps the solar system in its orbit around the sun. So it's the gravity, the force of gravity that keeps them in their orbit to keep moving and to keep moving. All right. Now let's get to weight and see the difference between weight and mass, which is important. Now, I've told earlier that the mass of an object is the quantity or the amount of matter present in it. So if you are looking to understand the mass, mass is just the quantity of matter present in an object. So it's that simple for you to remember. So you don't want to get confused about that. Now, on the other hand, weight, we've talked about it. Weight has to do with the force of gravity. Weight has to do with the force of gravity. And then the mass of an object will always be constant everywhere. So if you measure the mass of an object on Earth or on the moon, it will always be the same. But the weight of an object is not the same. So an important equation for you to remember in calculating the weight of an object is this. So it's mass multiplied by the gravitational field strength. And it's always important to keep the unit of all of this quantity in mind. The weight of an object is measured in newtons, the mass of an object is measured in kilograms, and the gravitational field strength is measured in Newton per kilogram. Now, you don't have to bother yourself. The value of this is always around 9.81 newtons per kilogram, or sometimes it's approximately 10 newtons per kilogram. So whatever you find in your question is what you will use. So this is not what you will calculate. It has already been determined. So you just make use of it to make your calculation. All right, so now let's see how to keep this formula in mind. It's important that you keep this formula, all of this formula in your mind. And this is a triangle for you to remember this. This is telling you if you are looking for the weight of an object, you just multiply the mass by the gravitational field strength. Okay, mass multiplied by gravitational field strength will give you the weight of an object. Now, but what about when you want to determine the mass of an object? Of course, the question may ask you to determine the gravitational field strength in another planet, because the gravitational field strength I wrote earlier is that of the Earth, which is always around either 9.81 newtons per kilogram or approximately 10 newtons per kilogram. So, and that is the gravitational field strength on Earth. On the moon, the value is different. So you could get questions that wants you to determine the gravitational field strength in another planet. Okay, but on the Earth, the value is constant. You will not get question asking you to do that. Okay, now what I'm saying here is to help you see, if you want to determine the mass of an object, that means, you see, you will be left with this, and that is weight divided by the gravitational field strength. So weight divided by the gravitational field strength will give you the mass of an object. The same thing goes for if you want to determine the gravitational field strength. What will that be? Good. It will be weight divided by the mass of an object. Weight divided by the mass of the object will give you the gravitational field strength. Okay, so now let's see some of the questions we have here and see how you can try your hands on them. I believe some of you will have started to do that already. These are still very simple stuff. What is the weight on Earth of a book with mass 2 kilograms? So we have the mass. The first thing, best way for you to keep a formula in your mind is to always write the formula every time you want to solve a problem. You want to find the weight, so you can say weight is equals to mass multiplied by the gravitational field strength. And since it says it's on the Earth, in this case, I would say take G to be 10 Newton per kilograms. Okay, so now the mass of the object is 2 and the gravitational field strength is 10. 2 times 10 would be 20 newtons. 20 newtons. You don't forget the unit. You don't forget the unit, okay? Now, what about the second one? In this case, you also want to determine the weight of the object, but the unit is given to you in grams. So whenever you want to convert, I will draw this for you. And please keep that in mind if you want to convert kilograms and grams. Okay. If you want to convert kilogram to gram, you multiply by 1000. And if you want to change grams to kilogram, you will divide by 1000. So divided by 1000, that will give you the mass of the object in kilogram. Is that okay? Right. So if you follow all that I'm saying, then it's good. It's good to help you. So can you divide that and see what you will have or what you get as the weight of the object on Earth? So if you divide the mass by 1000, that will give you 0.1 kilograms. So we want to find the weight. The weight will be mass multiplied by the gravitational field strength. And what is the mass is 0.1 multiplied by 10. And that, of course, will give you 10 newtons. So I will leave you to try your hands on the last two questions. So kindly leave your answer in the comment section. Remember to subscribe, like, and follow. And then I will see you in the next lesson. Bye.